Hi everyone, this is lecture video 23 and we will be covering concavity and curve sketching in this section. As you remember, we have seen how the first derivative tells us where a function is increasing and where it's decreasing, and also whether a local maximum or a local minimum occurs at a critical point. Now, in this section, we see that the second derivative gives us information about how graph of a differentiable function bends or turns. With this knowledge about the first and second derivatives, coupled with our previous understanding of asymptotic behavior, we can now draw an accurate graph of a function by organizing all these ideas into a coherent procedure. We give a method for sketching graphs and revealing visually the key features of our functions. Okay, look at this figure, please. The curve y equals x cubed rises, increases as x increases, but the portions over the intervals from minus infinity to 0 and 0 to plus infinity turn in different ways. As we approach the origin from left along the curve, so over this portion, the curve turns to our right, you see, and falls below its tangent lines. These pink lines are the tangent lines, and our curve falls below its tangent lines over this part. Here, the slopes are decreasing. If you follow the tangent lines, you will notice that the slopes are decreasing. This means what? Slope is the same as the first derivative, remember? So first derivative gives us the slope. And since we understand that slopes are decreasing, that means first derivative function is a decreasing function. Now, take this as your original function and take one more derivative of it. Okay, so you obtain second derivative. If a function is decreasing, here we will see this as our original function. If it is decreasing, what happens to next derivative? It should be negative, right? So then over this arc, over this portion of the curve, where the curve lies below the tangent lines, second derivative is negative, right? So this, if your curve lies below the tangent lines, it is called concave down, and this happens when second derivative is negative. So then I can write here that f is concave down. Then look at this part, please. Over the interval from 0 to plus infinity, as you can see, if you move away from the origin along your curve towards the right, the curve turns up to our left like this and rises above its tangent lines. So this kind of bending, turning behavior is called as concave up. And here what happens if you analyze the slopes? Over this portion, slopes are increasing. So first derivative gives us the slope information. That's why you can say that first derivative is increasing function. If you take one more derivative, what happens? Okay, let's take one more derivative. We see that this function is increasing function. Then the next derivative should be positive, right? Should be positive, and here over this curve, bending behavior is concave up. So concavity information is related to the second derivative of your function in this way. If second derivative is positive, your function is concave up. If second derivative is negative, your function is concave down. So let me put a quick summary here for you. Okay, summary. So what we have about the first derivative function, if it is positive, your function is increasing. If first derivative is negative, your function is decreasing. What do we obtain here about the second derivative? If second derivative is positive, your function is concave up, just like here. If your second derivative is negative, your function will be concave down, just like here. Okay, so this is our summary box, and this box summarizes what we have just learned about the first derivative and the second derivative in the previous two sections. Okay, so let's move on and use this concavity test for a function in an example. Okay, these are what we have written above. If first derivative is increasing, we already covered there. Your function is concave up. If first derivative is decreasing, your function is concave down. Then you can relate this information to the second derivative function. If it is positive, your function concave up, negative concave down, which we have already summarized here. Okay, so let's move on. Look at these two examples, please. We already analyzed y equals x cubed curve, but let's also do the second derivative computation here to see if this happens or not. So first derivative is 3x squared. Take one more derivative, it is 6x. And then we can easily create the sign diagram for the second derivative function. Before 0, second derivative is negative. After 0, it is positive. You know, this is the expression. If second derivative is negative, what happens? Your function is concave down. If second derivative is positive, your function is concave up. So from minus infinity to 0, you have a concave down graph. From 0 to plus infinity over here, you will have a concave up graph. So on this portion, second derivative is negative, and on this portion, second derivative is positive. And look at this curve y equals x squared. Compute its derivative, please. Like this. Its second derivative is 2, which is always positive. It is constant, so always positive. This tells us what? Since this is always positive, always greater than 0, our function will always be concave up function. It's always concave up, just like you see here. Okay, so let's move on. Let's look at this example. Determine the concavity of this function. How do you determine concavity? You will compute second derivative. So first derivative is what? Derivative of sine function is cosine. Second derivative of cosine function is sine x. And we are analyzing these derivatives on the given interval from 0 to 2 pi. So let's find the critical points of the second derivative function, right? So when this is 0. Sine x is 0 when x is 0. Since, you know, this is a periodic function, if x is pi, sine x is again 0. If x is 2 pi, sine is 0. And let's create the sine table for this second derivative function. So what we have, by the way, there are more roots of this function, obviously. It goes at every point like k pi, sine values are 0. But since our interval is a finite one, restricted one, we just have 0 pi and 2 pi, which lies in this interval. Okay, then insert them to your table. We are interested in over this interval, and these are the critical points, 0 pi, 2 pi. At all those points, second derivative is 0. And from 0 to pi, what about the sine function? You know, you can easily detect the sign of the trigonometric functions by looking at your unit circle. So from 0 to pi over here, sign values are positive. Okay, over this yellow shaded part, sign values are positive. From pi to 2 pi, which is here, sign values will be negative. From here to here, sign values are negative. That's why, by the way, this is the angle 0, this is pi and 2 pi. So from 0 to pi, sign is positive. There is another extra negative sign in front of it. That's why I need to put negative sign here. From pi to 2 pi, sign values are negative. Multiply one more negative sign here. That's why I need to put positive sign here. And when you detect, after you detect the signs of second derivative function, then you can put concavity information for the original function. Negative means concave down, positive means concave up. Okay, concave down function you expect over 0 pi interval, and you expect concave up function here. So let's verify all those information on the graph. So from 0 to pi, we expect a concave down function. You see, this is a concave down shape. And from pi to 2 pi, we expect concave up function. So you see, this banding is a concave up banding. Okay, that's how you detect. Let's move on. A point where graph of a function has a tangent line and where the concavity changes is called as the point of inflection, okay? To have a point of inflection, you need to have two things. First, tangent line should exist. Second, concavity has to change. Concavity has to change, meaning that second derivative should change its sign. So let's write this definition in a more clear way. So let's say we have a point C and second derivative of the function changed its sign there from negative to positive. For example, then your function f will be concave down over here and concave up over there. Since concavity changes here, concavity changes means second derivative changes its sign, okay? Change sign. If this happens, then you can call this point x equals c as the inflection point. Okay? And the situation may be also like this one. Concavity changes, but this time second derivative will change its sign from positive to negative. Then your original function will be concave up and then concave down. Since concavity changes here, in other words, second derivative changes its sign, then you can call this point, okay, d, let's say d, x equals d, here again an inflection point. Okay, inflection point is a new definition for us. It is the point where concavity changes. In other words, where second derivative changes its sign. If second derivative changes its sign from negative to positive or positive to negative, then that point is called an inflection point as long as you have a tangent line there, okay? So here is a remark for you, very useful one. At a point of inflection, either you have second derivative 0 or second derivative fails to exist, okay? So either at this C or D, either you have second derivative 0 or you may also have second derivative fails to exist. Okay, they may be 0 or second derivative may fail to exist. This may also happen, okay? So this is a very useful remark. Let me try to emphasize it with bold pens. If second derivative 0 or fails to exist, then that point x equals c is called an inflection point, as long as the second derivative changes its sign, okay? So let me write in a better way. Okay, I will write it like this. X equals c is an inflection point. If you know this information, then you know that either second derivative is 0 or second derivative at this point fails to exist. Okay, let's move on. Look at these two figures, please. You have x to the power 5/3, and we want to understand whether this function has an inflection point or not. So we will look at the second derivative, okay? So first derivative is 5/3, x to the power 2/3. One more derivative. So you will get 10/9, x to the power -1/3. In other words, 10/9, x to the power 1/3. And as you can see, second derivative is undefined. At which point? At x equals 0. So this point is now a candidate for the inflection point. To call it as an inflection point, you need to verify that the second derivative changes its sign there. Okay, so you need to create the sign table for the second derivative function. Okay, this is your expression. Before 0, if you insert, before 0, what happens to the sign of it? If you insert negative values, you will get negative. If you insert positive values, this expression will get positive. By the way, this is the special sign that we put two parallel lines to indicate that second derivative is undefined there. Okay, it is not 0, but undefined there. So as you can see, second derivative changes its sign here, right? Concavity changes. It is concave down first, and it becomes concave up. So concavity changes, meaning that second derivative changes its sign. After you verify this, then you can finally conclude that x equals 0 is an inflection point. Okay, so you see, this is an inflection point of this graph at which the concavity changes, okay? And before this point, you see that you have a concave down graph. After this point, you have a concave up shape. After you verify this fact, which is the following, second derivative changes its sign, then you can conclude that you have an inflection point there. Okay, let's look at the next example, which is x to the power 4. Compute its first derivative, compute its second derivative, and let's see if this is 0 or undefined at any point. Second derivative is 0 if x equals 0. This is an candidate for an inflection point now. To verify that it is in fact an inflection point, what you do, you will check whether concavity changes at this point or not, whether second derivative changes its sign or not. Before 0, what is the sign of the second derivative function? Since you are taking square here, no matter x is positive or negative, you will always get positive values, right? And here, second derivative is 0, so concavity doesn't change. Okay, concave up, y double prime, second derivative does not change its sign here. Concavity doesn't change, that's why x equals 0 is not an inflection point, although it makes second derivative 0, okay? So like this. You have to verify if the second derivative change its sign or not to detect your inflection point. Okay, inflection points occurs when second derivative is 0 or undefined. Then you have to verify whether it changes its sign or not. If concavity changes, then you will have an inflection point there. So for this graph, there is no inflection point here. Okay. So let's look at this figure now. Before the origin, from the shape, you understand that this is a concave up graph. And after 0, you see that this is a concave down shape. So at the 0 point, there is a vertical tangent of this graph, meaning that, okay, vertical tangent. Then you can call this point as a point of inflection. By the way, at a vertical tangent point, first derivative is undefined, okay? We may also have this kind of inflection points where first and second derivative fails to exist, okay? If first derivative is undefined, obviously you cannot find any second derivative. So this is an interesting example of an inflection point where first and second derivative of functions fails to exist. Okay, let's look at second derivative test, then I will stop. If the first derivative of a function 0, just like we have here, you know, at this point, f prime c is 0 at first derivative because you have a horizontal tangent and the horizontal tangents have 0 slopes. And before this point, look at the shape, or at this curve has a concave down shape, right? Second derivative, this is a concave down shape, meaning that second derivative should be negative. If this happens, if you have a horizontal tangent and if your curve is a concave down curve, then obviously at this point, you understand that before that point, second derivative is positive. Sorry, if this happens, let me say it in this way, then you see that this is a local maximum point, okay? And the other way around may also happen. If you have first derivative 0, okay, we are analyzing this part now. If you have first derivative 0, where you have a horizontal tangent, and if you have second derivative positive, what does this mean? You have concave up shape. Then this point is obviously a local minimum point, right? Local minimum point, just like as stated here. And if both of them are 0, then this kind of test fails. And this is another way of detecting whether you have a local max or a local min at a point. And this is called as the second derivative test. So this is our local minimum point. First derivative is 0, obviously. And since it is concave up, second derivative will be positive. Okay. So I stop here. Thank you for your attention.